software side. Here we are of the electrical vehicle. Here we are working on the on the vehicle and in the infrastructure with the deployment of new 5G technologies. And here we are working more on a larger scale, at the scale of the city or even the, I would say, a country, small country. And of course, we have some interdisciplinary projects, mainly like EU projects that are that connect the three departments. We also provide training and I would say innovation through spin-offs, and we also have a dedicated business unit. So our partners, so as I said, we are a private-public partnership. Sorry, this is a pretty crowded slide, but what you need to remember is that we have our founding members, which are industry and academia. We are funded also by the French government and the European Commission, some of our projects, and we have around 50 to 60 private sector members from the automotive, the transport, telecommunication, road infrastructure, aerospace, digital services, insurance, and with the academia and the local authorities. So in France, local authorities have a very big say in heavy infrastructure, and having them around the table is very important. So we are organized in several, as I said, 3 main departments. Each department has several research projects. So in my department, we focus on electrification in a large scope, not only mobility, but also aerospace. So I would say aeronautics, so the electrification of airplanes, for instance. And we have 5 main objectives. So first objective is very automotive oriented, is to reduce the cost of e-drivetrains through removing rare earth materials, magnets, simplifying production of mainly the electrical machine and the power electronics. We also work on the increase of performance of e-drivetrains. So here we develop technologies around components, power electronic components. So everything that is new in the semiconductor industry, like GaN and silicon carbide and gallium nitride components, and all the challenges they bring in order to have a more compact and more powerful power electronics. We also, so this is the main topic I will be presenting, the range to mitigate EV range limitation through wireless dynamic charging. We also study for the wired charging, basically the interaction that has to be done, the integration between the grid and the vehicle. So if you want to do some kind of smart charging or bi-directional charging with the grid, you have to have a vehicle that can connect and communicate with the grid in order to know whenever it has a window to charge or it should be giving back energy to the grid. So we also study these, this topic. And finally, we have a focus on energy optimization and thermal management. So everything that has to do with electric mobility, as we know, we don't have a internal combustion engine, so every time we need to heat or cool down something, we eventually the cabin or the power electronics, we need to get this energy from the battery, which drastically reduces the range. So we develop tools, simulation tools and experimental protocols in order to study that and optimize this energy consumption. So these are the 5 main objectives, and today we will be focusing on mitigating the range limitation of electric vehicles. So this project is called VERA, for electric vehicle without a limitation on range limitation. So some context, I think that the first beginning of this day, you had much of this context, and I would say the economic and especially the climatic impact of electrifying transportation systems. So we are confident that the EVs are one of the main players in the energy transition. And in France, up to recently, we had very major big incentives for the people to buy electric vehicles. And we are having a very big deployment of charging points. So we have a roadmap of 7 million charging points in 2030. So the government, the European Union and the government are heavily subsidizing the deployment of EVs. And if you want to deploy EVs, you have to have the infrastructure that is able to charge these EVs. So, as I said earlier, we look at these questions, so the charging infrastructure, but we also have a somewhat longer vision about how EVs can be charged and should be charged. So, you have I would say, the range problem. In order to address this, you have the recharge infrastructure of EVs, which we call in French IRVE. And the idea here is to say, okay, we can have lots of high power charging in order to reduce the charge time of an electric vehicle. But is it the best way, the best user experience, and the best way to be stopping in order to recharge? Wouldn't it be possible to mutualize the infrastructure? Because when you have a charger, only one car can charge. Is it possible to have some way to charge several cars at the same time without having several chargers? Would it be also possible to reduce the battery size of the vehicle? Because if we can charge while we are moving, we can have less battery weight and then be more energy efficient. And of course, this will have a very big impact on the user experience and the habits of users, especially as we can already see it in tramways, where, for instance, some cities don't allow for cables or visual pollution in historic areas of the city center. So this is why we started investigating wireless charging since 2014. And we, as you can see here, identify four, I'd say 6 use cases. So you have the lightweight electrical vehicle with static charging. This is what is already being proposed by, so you can see this on your phone. Your smartphone can wirelessly charge statically. You can also have this, I would say BMW have recently rolled out a very high-end model with this option. You have the dynamic extra-urban charging. So this is mainly on the highway. And you have the urban, so the city wireless charging. So this is for the light EVs, and you have the heavyweight EVs. So this is everything from heavy transport to light-duty vehicles. And our objective here is to provide technologies in order to enable these wireless charging systems on these use cases. So the question will be, well, how does it work, wireless charging? It's not very complicated from a electrical and electromagnetic standpoint. Conceptually, it's quite easy. So you have a track, and on the track you have coils that are embedded in the road, and at the car side you have a receiver coil. So it's the same setup that you would have on your charging pad and your smartphone, but a bit more power and a bit more, I would say, heavier. And so you will go from the power grid to an AC-DC converter. So you have to filter out everything that we will be doing on the high frequency side of the circuit. Then once you go to DC, you will have a second stage of DC to AC conversion, but this AC will be around 85 to 90 kilohertz in order to have the system radiate magnetic field, electromagnetic field from one coil to another without having any connection between them. So you have the ground coil, okay? So these are the track components. And on the EV side, you have the EV coil with the charger, and that is connected to the battery. And the power transfer is done between these two coils through the air. Okay? So this is, for instance, the case for a car with a single coil on it and several coils that are on the track. As you can see here from the lights, so the green color and the blue color indicate that these are the coils that are, so the green coils that are the coils that are active, and the blue coils that are the coils that are ready, standby, and all the red ones are off. So the track only produces wireless electromagnetic field when it detects the equipped car. So this is the I would say broad concept. So in this project, we are funded, as I said, by Renault Group, PSA. So PSA is Peugeot, Citroën, and Opel. EDF. So this is the French national energy provider, and the French government as well as the department. So this is the Versailles area, the department in charge of the Versailles area. So as I told you, the project in a nutshell, so we study the techno-economical evaluation of wireless charging systems. So how much power should I provide in each of the use cases? How do we characterize and test and evaluate these systems? Because if you can look at the literature and some of the startups already are proposing some systems that they are showcasing in certain areas of the world. And we also develop our own wireless charging system. And the most important part, I would say, from an industrialization point of view, is the interoperability and standardization, because the same track should be able to charge several cars. So some of our work is based on mathematical modeling. So you have lots of modeling, simulation, 3D, so 1D, 3D simulation, but also experimentation activities in the lab. So you can see here we have a robot with simulated tracks, so several coils on the table and one coil that simulates the car, and we can characterize at each point and measure different characteristics, as you can see in the video here. So you have the robot that is moving, and at each point we are using some magnetic field probes in order to characterize the radiating magnetic field, because we have to also be very compliant with safety regulation. So here you can see some characterization that is being done, and the fact that we have this robot, we can also optimize the functioning of our system with different, as I told you earlier, these are the coils. Here you can see them that are in the track, and of course you can have asphalt or concrete, okay? And we should be able to characterize the impact of different parameters like material, alignment, and air gap on the energy transmission. So we have already done prototypes. So this is a small prototype that we did earlier in around 2016 and 2017, just to showcase the technology. So this is a track. Each box here is an inverter, and inside the track you have different coils. So the power electronic box is connected to one coil, and you have a coil in the Twizy. And here the Twizy, when it goes up on the track will emit the electromagnetic field that will be received on a coil in the car. And of course here, because so we need a visual representation of the power transfer. So you have the very powerful lights that turn on behind the Twizy. So this is a small system, 3 kilowatt, that we used, and we used this knowledge to develop. So this is still under development. As you can see here, a 30 kilowatt system. So here we are not, we haven't put it on the car yet. So, but we can see here we have 4 coils that represent the track. Each coil is connected to its own power electronics, and you have the receiver. And the robot allows us to do repetitive passes on the track in order to measure the properties of the system and the performance of the system. As you can see here, we have 30 kilowatts. So 30 kilowatts, if you are in an urban environment, 1 minute on the track will provide you 6 extra minutes of range in an urban scenario. And on the highway, it will charge at, I would say, 7 kilowatt rate. So it's like you are traveling on the highway, you are not depleting your battery, but you are charging at low power. So 30 kilowatts is a modular design that can be used on light cars and intermediate heavy light duty vehicles. So you can see here, the most interesting thing is the efficiency, because you can see here that we managed to run on efficiencies that can attain 90%. And this was one of the very big challenges at this stage of the project. So what? So the idea is to go and install these in the tracks. So we've already had, as I told you earlier, a very big European project from 2014 to 2017, which was called Fabric, in which we installed a system. It was not our system, it was the Qualcomm system on a 100-meter long track, where we demonstrated the power transfer at 110 kilometers per hour for 20 kilowatts. At the time, there was also a very big research around the vehicle to infrastructure communication, because the track needs to know every point where the vehicle is in order to activate or deactivate the coils of the track. And here we managed to showcase the feasibility of the technology. So with the developments that we've been doing since 2017 on this 30 kilowatt system, we managed with our partners to have this European project that started at the beginning of this year, which is called Insight EV, which focuses on user-centric charging infrastructure. And 2 of the use cases, so you have 7 different use cases throughout Europe, as you can see here. And 2 of these use cases, one of them will be in our test track at Châteaulet in Versailles for highway cruising. And there will be a use case. So use case number 3 will also deploy a track in Paris. So there will be a 2 times 25 meter track, inductive track for charging the equipped electrical vehicles based on our system. So there will be a track for 30 kilowatts in Paris. So this is basically what I wanted to show you, is the state of the development of this technology. And we are pretty confident that this technology will start to make its way slowly but surely, because it involves a very heavy investment in the infrastructure. And at the moment, we can see that there is a nice opportunity to deploy it on bus lanes and in the city where we have good traffic and where it can be used with different users of the road. Thank you very much. All yours for any questions.
Thank you very much, Rolf. Indeed, it was a very, very interesting presentation. We thank you for presenting not only the DECOM, but also some of your projects, which I would say enlighten some of the technology, the wireless power transfer technology, which is quite promising, according to my opinion. Thank you very much. We can proceed now to the next presentation, as we are a little behind in our schedule. It's the presentation by Easy Europe, which is partner in this partnership in project EDRIVETOUR. Presentation will be by Mr. Van Kai Nguyen. Okay, perfect. So once again, I would like to apologize for this delay, and we'll be glad to hear your conception about sharing electric mobility. You have to unmute your microphone. Could you unmute your microphone, please?
Do you hear me now?
Yes, we can hear you now.
Okay, sorry. Good. And do you see my screen? How can I share my screen? No, it's not. I'm not. Sorry.
We can see your screen.
But the presentation. Do you see my presentation? Okay. Do you see my presentation now?
Yes, yes, yes.
Okay. Okay. So I'm sorry for this IT problem. So I'm replacing Madame Sun Nguyen, who is